So much for having me. And I'm actually right down the road, so same time zone and everything works out great. So yeah, like Joe said, I'm from formerly Carnegie DTM, now Carnegie Earth and Planets Laboratory, because Earth is a planet. I'm talking about some work I've been doing in collaboration with Lisa Quintana at Goddard, and bringing in some other work that I've done with a bunch of other collaborators. So list them on this slide as well. So yeah, the first thing I'll show is a plot everyone's seen. We're looking at a bunch of exoplanets in orbital period, planet radius space. And I've color coded the ones that are around low mass stars, or so-called M-dwarfs here. Things like less than about half the mass of the sun in red. And if we look at where the habitable zone is for sun-like stars, you see there's not very many Earth-sized planets in the intersection of those two boxes that we found on Earth-like orbits around sun-like stars. This is why M-dwarfs have been such a hot topic in the last 5 years or so, because if we look at the habitable zone around M-dwarfs, it's much closer to the star. We've observed a lot more Earth-sized planets in the intersection of those two boxes, the red dots, around M-dwarfs. So they're the most common type of star. We think these are the most common type of Earth-ish size planets, and particularly lucrative because they have super deep transits, as everyone probably knows. So they're prime candidates for follow-up observations, atmospheric characterization. So there's been a lot of emphasis lately in understanding the potential for habitability around M-dwarfs in comparison to habitability around sun-like stars. But the formation of these planets is still fairly understood. And there's another big problem. So if you watch College Game Day, you'll get this joke. If not, not so fast. It might seem really lucrative, but there's a lot of hazards that these planets around small stars may or may not face. In particular, there's a lot of hazards that these planets' atmospheres might have to overcome. So first of all, low mass stars are much more active than stars like the sun. So as we go along the M-dwarf mass spectrum, or decreasing in mass from left to right in this plot, we look at flare activity from Kepler stars. It increases as you go down in mass. These planets are also close to the stars. I'm sure you've seen talks before about tidal locking and tidal heating. That's a problem for these planets as well. And also the XUV fluxes, particularly early in life, are much higher than we think at least the Earth underwent. And finally, unlike the sun, which formed and cooled in a matter of millions of years, low mass stars have extremely long cooling timescales. So the habitable zones themselves take upwards of like 1 billion years to reach their final location. So a star that is in, or a planet that's in the habitable zone of the M-dwarf now, it didn't necessarily get there for like a billion years or so. And a lot happened in the first billion years of these planets' formation, particularly in the solar system as we understand it. So if we put the TRAPPIST planets down on this same plot, and we evolve them through 1 billion years or so, they're getting zapped by flares and XUV radiation. The 3 that are in the habitable zone now don't even move there until 1 billion years or so. So through this process, it's very easy we think, to lose a primordial atmosphere or desiccate a primordial atmosphere. And if you had water in the atmosphere, zap water down and lose all the hydrogen, and then the oxygen combine with less desirable things, and you get a bunch of carbon dioxide or something that wouldn't be as hospitable to life. So our research question is really, if you lose an atmosphere, is it possible to replenish it and make these very, very numerous planets habitable? So there's 2 ways, and you might have seen talks about this, where you could develop a secondary atmosphere. The first, you could develop a secondary atmosphere by outgassing volatiles that were initially endowed in the planet in its formation. So if these planets formed with a lot of water and they had a water cycle like on Earth, where you have volatiles in the mantle that are degassing into the ocean and then making their way in the atmosphere, and then cycling their way back down through granite back into the mantle. This could work. Now, the caveat on this is, first of all, we don't even really fully understand Earth's own water endowment. The water in the mantle of the Earth is extremely uncertain, and we think, compared to other terrestrial materials, even in the solar system, the Earth is extremely dry. The Earth actually does not have a lot of water. This is almost a problem, as we'll get to in subsequent slides, in our understanding of how the Earth formed, Earth-like planets form. We make them too wet. So if these planets form, like Earth, maybe not, but if Earth is just strangely dry, like it kind of seems it might be, maybe this works. So the other option is we could deliver material late. We could just like on Earth, Earth didn't just stop forming and then experience no further impacts, as we see from the moon, for example. There was a lot of debris left over in the solar system after the planets formed. That's how you got all the major basins on the moon. So Earth was getting shellacked with material from throughout the solar system. And we really think, and this plot's from a recent paper on the evolution of the Earth's atmosphere, we think the Earth's primordial atmosphere was completely reshaped and reconfigured by delayed bombardment. And you think comets would be the prime source of it, but it's an extremely stochastic effect. You have stuff coming in on crazy orbits from way outside of Neptune's orbit. So comets aren't the largest driver in the reshaping of Earth's atmosphere, we think. It's actually not even asteroids from the main belt. It's just leftover planetesimals. It's leftover junk from the formation of the planets. On Earth, this occurred over billion-year timescales. So that same sort of timescale as we're looking to source a secondary atmosphere in. So maybe this is possible on an M-dwarf. And that really leads to the main research questions that we've been looking into. So first of all, is it possible for mode 1 for these planets to be extremely wet, to be endowed with large volatile inventories in their formation to where they can outgas secondary atmospheres on billion-year timescales? Or number 2, if not, or even if 1, is it possible to have a leftover debris field, just like we think was around the sun after the Earth's formation, that could source late delivery of small bodies that were volatile rich on billion-year timescales? So how do these planets form, or how do we think they form? Well, we sort of understand planet formation in the solar system, and by extension, we kind of understand it around sun-like stars. And as we map these processes down to M-dwarfs, there's fewer and fewer papers, and our understanding is much more vague. So we'll start with the solar system paradigm, and then we'll build out from there. So here's the solar system. We've all seen it before. We have terrestrial planets on the inside, giant planets on the outside. Here's the basic timeline for the solar system's formation. You start with a collapsing cloud of gas and dust, and then you form something like you learned in elementary school, and then there it is on one slide. Now we are talking about solar system formation. So let's put some more detail, some more granularity onto this, and then try and overlay M-dwarf formation on top of the same picture. So the first thing we can put on our basic timeline, so we know from looking at planet forming regions that the majority of the solid material is in the form of dust, just kind of like the stuff that's built up on everyone's desk right now at work, because you haven't been there in a while. We know from just this extreme overabundance of IR radiation when we observe these things, that all the solid mass is in dust. So time zero, or before time zero, we start with all the solid mass in dust, and we got to build it up into planets. Next thing we can put on this timeline, we know that the gas is only around for a fixed amount of time. We think only just a few million years. So if we look at planet forming regions, or star forming regions, regions that are forming a bunch of young stars, and we can look at the velocity dispersions of these things and get a rough age on them. We see as they get older and older, you have fewer of these IR excess sources. So these gas disks, these planet forming regions, they really only last for, we think, a few million years. We think maybe 2 to 5 million years in the solar system at least. So we can put 2 more things on this plot now, on this timeline. We know that all the gas has to be gone within a few million years. And if the main ingredient of the gas giants is gas, they have to form before that in just a million years or so. So After just a couple million years, the solar system looked something like this beer here. It was flat. It was gasless. So the next thing, we can look into the meteorite inventory. And we know from a specific class of meteorites, the so-called iron meteorites that are presumably, we think, just fragments of large differentiated objects that were able to consolidate all their iron in their core. Some of these things have dates that actually are around the same time as the oldest materials that we can date in the solar system, the CAIs. So we know sometime around time zero, we already started forming big, large differentiated objects. The other thing, next to the Earth and the Moon, maybe the best estimate of a geological accretion time that we have is from Mars, from a handful of Martian meteorites. We know that Mars formed fairly quick, at least with respect to the Earth. Mars accreted in just a few million years, maybe 10 million years at most. So next thing we can put after the gas goes away is we're able to form a Mars. And then finally, we can compare the Earth and the Moon's the mantle effectively with hafnium tungsten dating and get an estimate of when the moon forming impact occurred. So the final large accretion event on the Earth, there's a little uncertainty in this, just based off what's the difference in bulk composition of the bulk silicate Earth versus the Moon, but kind of our best estimate puts that at occurring within about 50 million years of the solar system's birth. So kind of an order of magnitude longer than Mars' accretion. So put Earth on here, so now I get the whole timeline filled out. And again, in one slide, that's how we go from dust to posting on Facebook and Twitter about how planets form. So now in just 2 slides, I'll summarize how we go from dust to large planet-forming objects. And this is still a very active field of research, but it's difficult to get dust grains to stick together past like little rock pebble size things we call pebbles that look just like presumably like stones you'd find at the beach. So there's a few ways we can get beyond this. On the right, you can directly gravitationally collapse things and form large asteroid-sized things. And we think what's called pebble accretion. These pebbles, as they're orbiting the star, they feel a headwind of gas. So just like if you're driving with the windows down, you put your hand out, they feel this headwind. It's drag. It moves them inwards. These pebbles are constantly piling up and moving inward and raining down on these objects presumably formed by a gravitational collapse. And you can form larger, 10, 100 kilometer scale objects, which we call planetesimals. And once you're able to get planetesimals, we can really kind of push play on our simulations and make these things grow all the way into terrestrial planets. So you put a bunch of planetesimals in a simulation and they're going to experience runaway growth in 1,000 to million year timescales, grow up into Moon to Mars size objects. And there's a strong radial dependence on this. So in the vicinity of like Mercury around the sun, you're able to form things almost half the size of the Earth in just a few 100,000 years, whereas it takes much longer as you go further out. So we know from that this process is not really what formed the giant planets. You really need really efficient, pebble accretion and gravitational instabilities to form giant planet-like things. But this gets us the terrestrial planets building blocks and gives us this basic picture of how we've studied terrestrial planet formation in the solar system for the past 25 or 30 years. You have the giant planets fully formed on some version of their modern orbits and a bunch of leftover junk inside of there that's represented by this distribution of larger Moon to Mars sized embryos and smaller asteroid-like planetesimals. And we think this general picture is pretty well supported with the timeline of at least the timelines that we infer from the meteorite inventory. In the last 4 or 5 years, there's been this big new development. Really, if you plot these 2 different chondrite groups, the non-carbonaceous and the carbonation chondrite groups in any of a dozen or so isotope spaces, every single thing separates wildly out on 2 different sides of the plot. And we really think this means that these two groups of planet forming material were separated very on in the early solar system's history. And the most likely culprit is Jupiter grew and separated these inventories. So this whole picture, everything's kind of coming together, you know, in the last 10 years or so to really back up that this is the picture you had when the terrestrial planets were forming. And people have been simulating this by just, you know, running a simulation where we put the giant planets down and we put a bunch of terrestrial forming material into our numerical integrator and we let the computer work for us. And what you're seeing here, I'll show a bunch of videos like this. You're seeing semi-major axis on the x-axis and the eccentricity of orbits, how elongated they are on the y-axis. And you see in the right sort of time scales, that 50 to 100 million year time scale as we think the Earth formed in, kind of formed 4, in this case 5 with an extra planet out in the asteroid belt. 4 terrestrial planets sort of right where they're supposed to be. And really the main shortcoming of this that people have been working on, myself included, for the last 20 years or so, the big shortcoming of this model is, you see here, the planet that forms out by Mars is the biggest planet here. Mars is only like 10% the mass of the Earth. It's called the small Mars problem. And that's not the point of this talk, but something important to understand that we really are able to take from solar system science and overlay onto exoplanet science is that we really have 2 reshaping mechanisms to fix these problems in the solar system. And we think that these same processes are the same processes that are responsible for reshaping exoplanet systems as well. Play with these same dynamical processes to reproduce observations. So the first option to fix the small Mars problem, to give you a small Mars, is that we know the giant planets, their orbits migrate. They migrate within the gas disk. They move around just like those pebbles, and for other reasons as well. They can carve out gaps and migrate inward and outward. And if you let Jupiter migrate inward after it forms, this red and blue dots here in this first video is the terrestrial forming embryos and planetesimals. You can concentrate everything into a very narrow, what's called like an annulus. And then Saturn starts to grow and falls into resonance with Jupiter and pulls it back out. Beyond the scope of this talk, but you concentrate all the terrestrial forming material in an annulus. And then if you press play on that, you're able to get a small Mars, sort of where it's supposed to be. And the second option is on the right. We also think that the giant planets' orbits destabilized after they formed. And we think this also explains observations of giant exoplanets as well. So if you use the best solar system instability model and have that occurring in conjunction with terrestrial planet formation, it's a solar system instability model, which you heard maybe referred to as the NEAS model. This explains a lot of things about the outer solar system. Well, if this kicks off while this giant impact phase, this phase of terrestrial planet formation is happening, kind of truncate the disk as in that other video and really limit Mars's growth as well and get something that looks like the solar system. So as I said, you know, we really think both these processes, we have every reason to believe that they were both at play, and it's really just a debate of, you know, to what degree they sculpted the solar system. So we think these processes probably, you know, these dominant giant planet migration and giant planet instability processes, they really sculpt all solar systems and are responsible for making our own solar system look different from the ones that we observe. So now let's map this down to M-dwarfs. So how do we think habitable zone worlds around M-dwarfs might have formed? Did they form like the solar system, or did they form differently? Well, there's 2 real options, A or B. So the first is, we refer to this as kind of migration. And this is kind of the best explanation for super Earths around sun-like stars right now. So they could have formed by forming further outward like the giant planet cores did, but instead migrating inward, not accreting gas. These lines are lines of constant zero migration. So they fall inside of these lines when they reach a certain mass, and they can move outward. So they could form like that. They could form not where they are, not in the habitable zone, and they could move on inward and then become these habitable zone, you know, Earth, super Earth type worlds. And they could form like the solar system terrestrial planets did, just right from the ground up, just a lot closer, right? You could put that same disk of embryos and planetesimals near the habitable zone around a low mass star, and this this process happens a lot quicker because the orbital periods are quicker. So in just a few million years, you can turn this distribution of embryos and planetesimals into a system of 5, 6, 7 Earth mass planets or larger planets if you start with more material. So this works as well. And I'm not really going to get into the debate of which one or another. I'm just going to make the argument that no matter which one you have, you are going to have debris left over afterwards. If you watch in that first video, a couple of those planets smashed into each other and you had these massive planet scale impacts, these things I refer to as giant impacts. And when you simulate these things with hydrodynamical models, they should be kicking a bunch of debris out into the system. A lot of this is going to be in the form of dust. Some might be in the form of massive particles. And you also see in both videos, you have a few kind of smaller objects that get stranded, and these can get, represent that kind of leftover population of material that might be left over to come back in later and source late volatile delivery. So we ran a bunch of simulations, just like the first ones we showed you for the solar system, but mapping down to the M-dwarf system. The M-dwarf regime. I'll talk about later. We did some models where we had a giant planet model. We put like a Neptune out there at 1 AU. We're starting to observe some of these with RV and with transits, and Neptune to Saturn mass planets around M-dwarfs at 100 to out to 1,000 day orbit. So we tested this, but again, we just used that same simple picture. Lay down a bunch of embryos and planetesimals, let the disk go all the way into the magnetic truncation radius, and let it go all the way out to kind of Neptune's hill sphere or region of gravitational influence. Put all the material down, try couple different, reasonable masses that are kind of consistent with, the empirically derived minimum mass extrasolar nebula for M-dwarfs. It's basically derived from, the occurrence rates of planets of different masses. And put it all in a simulation and ran a bunch of these and let it go. So I'll play this video here of one of our simulations. It made a system that kind of looks a lot like TRAPPIST-1. So we put a plot of it in the paper because it's a good looking one to show us a plot. But, we form, a variety of different types of systems, just like you do when you run models of this in the solar system. It's a very chaotic process. You get a wide range of outcomes, 4 to 10 planets or so, 1 to 2 planets in the habitable zone. If you start with less mass, you still form planets in the habitable zone, but they might not be big enough. They're not necessarily Earth-sized. And again, this is the primo plot here, a bunch of planets that have masses, really similar to TRAPPIST planets. The last 3 are pretty much exactly, and the second, third, and fourth, or C, D, and E, or if you change their order, they're almost exactly right. So yeah, just matching one system isn't that exciting. What we're really interested is, how can these models match the distribution of observed exoplanets, particularly multi-planet systems. If you've seen Sean Raymond, for example, give a talk before, you've probably seen plots like this before. All we're plotting here is the period ratios of successive planets in multi-planet systems around M-dwarfs that are, with 100 or so day orbits or less. Semi-major axis like less than 0.5. So potentially planets, in systems with planets near the habitable zone. So what's interesting about this plot is not what it is. It's more what it's not. If these planets formed by a convergent migration, we would expect this to look something more like this, where you have pileups of planets in so-called resonant orbits. So like 3 to 2 orbital resonance here, where 2 planets where their orbital periods are in integer ratios to one another. One of them goes around 3 times for every 2 of the other. This is this dynamically stable configuration unless you perturb it. Other common resonances that you could form these planets in, but this gray distribution of observations, it does not look like this. Some systems do. For example, if you plot the TRAPPIST planets, half of them that are in 3 to 2 resonances. So it looks like that red curve, but the observations don't universally. And what is this telling us? Well, it could be telling us a number of things. It could tell us that most of these planets form the way our simulations have them form, and particularly our heavier disks do a really good job of kind of matching this distribution. Or another option is they do form by migration, they do fall into these resonances, and then they subsequently get kicked out of them. So these resonant configurations, like I said, they're not necessarily stable to external perturbations. So if you knock one planet out of resonance, that's what we think happened in the solar system with the solar system's giant planets. You knock one out and then the whole system falls apart. So this is what's known for solar type stars, and explaining super Earth orbital periods is breaking of chains model developed by Sean Raymond and Andre Isidoro. So you take that first distribution I showed, that stepwise function on the left, the green and the red lines, and you let these things destabilize, and you can match the observations a lot better. So we're just arguing that our simulations are at least reproducing the observations in broad strokes. So then the next thing we looked at is that first question, right? Can these planets be endowed with enhanced volatile contents compared to the Earth? And the answer is not just yes, but resoundingly yes. These planets formed in situ, with or without giant planets, they are extremely wet. And the reason for this is just, if you start the snow line out at the same, disk temperature as where it would be in the solar nebula, and there's some problems with this, but dynamically speaking, as you go down in stellar mass, a point in the disk that's cold enough to have water in solid form and incorporated into these materials is that distance falls off as distance squared, whereas dynamically we care more about distance directly between two objects to get them to hit, or in particular orbital period, which Kepler's laws that falls off to the 1.5. So it's a lot easier for a habitable zone planet or on an M-dwarf to accrete something from beyond the snow line, something beyond the snow line around a 0.1 solar mass M-dwarf only has to attain the eccentricity of like 0.3 to smash into something in the habitable zone, whereas in the solar nebula, something in the outer asteroid belt would have to get eccentricity of almost 0.7 to hit the Earth. Now, a big problem with this is, like we said, these stars have extremely long pre-main sequence cooling times. So is this an accurate picture of where the snow line was as the planets were forming? Well, probably not. But also, these outer solar system or outer exosolar system planetesimals might have boosted volatile contents already if they're getting rained down by pebbles from the outer parts of their disk. So tentatively, is this possible? Yes, but there's a big caveat on it. We don't even understand water delivery to the Earth fully. It's still a big question of, why the Earth is so dry compared to our numerical simulations. So, the jury might still be out, but it is possible. So the next thing we noticed that is fairly interesting is, we talked about at the beginning of the talk, these leftover distributions of planetesimals and debris that might source late delivery. After you let these things evolve for tens of millions of years, you still do have a substantial population of debris that some of it, particularly out in this region, out past like our outer disk boundary of 0.5 AU, and something that looks like an asteroid belt analog. And this isn't necessarily a new revelation that you let the terrestrial planets form and you implant material from that region into the asteroid belt region. We think this happened in the solar system. It's really dependent on whether you have that giant planet out there or not. So if you do have a giant planet in our simulations, we form asteroid belts of comparable mass to the solar system's asteroid belt. Whereas if not, you can really put hundreds of times the material that we have in the solar system's asteroid belt out in a belt analog. And it's going to become important later too when we're talking about giant planets. So in addition to leftover planetesimals, what about leftover collisional fragments? Well, our first simulations, we didn't track collisional fragments. So we rewind those back, and we performed a whole bunch of other simulations of these final giant impacts. Here, the collisional fragments are in green. And we ran tens of thousands of these because they only produce a few fragments each, which in reality are going to kind of be tracers of the actual fragment population. And you let this thing go, you get some final fragmenting collisions, you strand some fragments, and we also were able to infer kind of a leftover collisional fragment distribution. So here's our data here, and we want to see what this leftover distribution of material, how it dynamically evolves in not our fictitious systems, but systems of real exoplanets. So we took a few interesting systems across M-dwarf mass spectrum. Of course, we had to do TRAPPIST that all have around an Earth-sized planet in the habitable zone. And you see that, particularly around like TRAPPIST, there's not a lot of fidelity in these plots, but we took all this material and we let it evolve for 1 billion years. And here I'm comparing in gray to similar simulations in the solar system from my previous work. But you see there's actually a similar number of impacts in these histograms. They're all buried to the left of the plot in the TRAPPIST simulations, the proximal ones. Because around these like 0.1 solar mass stars, all this stuff gets cleared out rapidly in tens of thousands of years. So you see a big discrepancy, even with like TOI 700, which is a 0.4 solar mass M-dwarf, big discrepancy in how many just total impacts you're having early on compared with like the solar system. But as you move further to the right in that plot, things start to kind of even out. Really, after 100 million years or so, you do start to get within orders of magnitude of the bombardment in the solar system. So, maybe this is possible. Did the same thing for our fragment population. And it turns out because all those fragments really concentrated out in the asteroid belt region, that's where they get flung out when they get, ejected from their stars. They either when they get ejected from the collisions, they either hit the sun or they end up out in that asteroid belt. So we did get a lot more like late impacts from these fragment populations and a lot less variance between our different planets that we looked at. And there's a huge caveat on this discussion of the collisional fragment populations, and that's that the way we model this in our simulations, it's extremely, our results are extremely dependent on our model assumptions, how we're treating fragmentation in our code. We really don't fully understand what role collisional fragments played in the formation of the solar system, for example, how much of this should be ejected in dust and how much in massive particles. So maybe take this all with a grain of salt, but I'm still going to try and draw some sweeping conclusions from it in the subsequent slides. So this is what we want to get at, right? In the final few minutes of my talk, we want to get at what is the probability in these systems. You have this late bombardment curve that we can fit some curves to, and what's the probability that we can have a late, large, very wet impact that might source a secondary atmosphere? So what would this go as? It would be something like the probability of having an impact, from that curve at a specific time, and we can get that from those simulations I just showed you. What's the probability that impactor originated at time 0 before the plant formation simulation outside the snow line? Well, we can get that from our initial plant formation simulations. And then what is the probability that thing is big enough to have a bunch of volatiles to source an atmosphere on like an Earth-sized planet? Well, that's not as easy to get, right? We have to make a bunch of assumptions. We have to assume how much total leftover mass there was, which there's a huge range. We can average out all our simulations. It's about a Mars mass, but there's a huge range in all the different simulations. So it's a huge variable there. And also depends on what's the size frequency distribution of objects that are left over after that process. And we can kind of get at that in the solar system. So by extension, we kind of try and map that to exosolar planets. But it's really the holy grail, right? What's the initial distribution, size distribution of planetesimals that form these planets, and then what's the remnant distribution in the solar system, at least kind of sources the asteroid belt. We're kind of, in a lot of fields are starting to sort of converge on the right answer. If you look at simulations of the streaming instability forming planetesimals, can sort of, turn all the knobs correctly in this plot here and get a good match to the actual asteroid belt's size frequency distribution, which sort of has this knee at around 70 kilometers. The other thing we can do to try and get at this, we can look at all the asteroids in the asteroid belt that don't belong to collisional families and presumably unprocessed by collisional processes over 4 billion years. This has more of a knee at 100 kilometers, which sort of supports ideas that planetesimals actually form big. And you start with this this distribution of 100 to 1,000 kilometer planetesimals, which form directly via the streaming instability. And then that gets processed over 4 billion years in the asteroid belt to make the belt size frequency distribution. So maybe something more realistic in these simulations is something that sort of looks like the asteroid belt with this heavy tail on it of these initial 100 to 1,000 kilometer objects. If we do this calculation, get this probability in the solar system, it's about 90% of the iterations. You can get a 100 kilometer impactor from well outside the snow line coming in after about 500 million years or so. And for reference, like the large basins on the moon, like the Imbrium Basin, for example, those were 100 kilometer scale impacts, and they happened 500-600 million years after the solar system formed. So this is kind of consistent, with the cratering record as well. So we do the same thing. We fit some curves to our bombardment curves from our leftover debris simulations, and we look at all these different systems of exoplanets. We made some loose constraints here. We want something to come in after about 500 million years or so. So at least the outer habitable zone within the main sequence phase is habitable. We want something like at least 100 kilometer impactor. Again, these are very, very loose assumptions. We probably need a lot more to reconstitute an atmosphere, but that'll get you about 1 Earth atmosphere worth of volatiles. If it's like, something of makeup like, asteroids in the outer asteroid belt. And you see, we don't get close here. All right, all these different systems, bombardment really only lasts for like 100 million years or so. So the answer to that second science question is sort of no, but if we kind of relax all assumptions, instead, let's look at that fragment population and let's relax the assumption that this impactor has to originate outside of the snow line. And you could maybe, if these collisional fragments are ejected from the surface of differentiated objects, they might be more volatile rich. So you can kind of wave your hands and you see, in some cases now we can kind of meet that constraint. But unfortunately, the answer is really no. It's very difficult to get bombardment to last that long in these systems. And really the reason for that is that, we don't have giant planets in those systems, or we don't think we do. In the solar system, things are still hitting the Earth today because there's all these resonances, there's all this fine structure in the asteroid belt. If you look at a plot of the asteroid belt orbital elements, semi-major axis, and eccentricity or inclination in proper element space, see these huge gaps which are due to dominant resonances with the giant planets. And that's what's flinging stuff in to the near-Earth asteroid population today. So we think we need giant planets in these systems to be able to source significant bombardment. And that's something that can be constrained by looking at legacy RV data. Like people have done this for the TRAPPIST planets to try and put limits on what the most massive planet you could have that wasn't detected by RV. But something to keep in mind is, and I know about over time here, is that if you do have these asteroid belt analogs that get formed through this terrestrial planet formation process, while they could be extremely volatile rich, you see in the simulation of the solar system, as Jupiter and Saturn grow, it implants these outer solar system planetesimals, these icy rich asteroids that we observe today in the asteroid belt. They're also extremely fragile to these processes of giant planet evolution that we know happen, that I talked about earlier, migration and instability. If migration is too strong, instability is too strong in the solar system, you can wipe out the asteroid belt and the Kuiper belt entirely. Did some scattering experiments to kind of show this. If you just put everything in natural units and use different sized giant planet combinations and let them migrate or let them go unstable, for certain combinations, upwards of 60% of the belts are destroyed entirely. It's just being showed here. So maybe the preferred combination is actually a less massive inner giant planet and a more massive outer giant planet. That's really what would be preferable for being able to maintain an asteroid belt that could source this late bombardment with the giant planet friend. And these are things that we'll be able to constrain in the future too, as we're able to, with the ALMA expansion, with Roman upcoming, being able to probe further and further down and hopefully observe debris disks around M-dwarfs. but we're looking for this holy grail, right? We're looking for an Earth-sized planet with a giant planet friend at like 100 to 1,000 day orbit. I've been working with Fabo Fang, who is at Carnegie. This is pretty much my last slide here. Who's been doing great work. He has a pipeline that removes noise from RV data going back years and years and years to find all these undetected planets, and he's able to achieve like less than 0.1 meter per second precision, being able to find all these new super Earths in the habitable zone around M-dwarfs, but more importantly, really populating this region on that mass orbital period plot with those colored symbols, finding Saturn and Neptune analogs at like 100 to 1,000 day orbits around M-dwarfs. So we have a bunch of systems that we're interested in that have M-dwarf hosted habitable zone Earth analogs, and he's using this pipeline right now to see if we can find some giant planet companions. This is our best example so far, GJ229. It's like just barely an M-dwarf, a very massive M-dwarf, but it has a super Earth and a Neptune. So this is kind of a case study for where you could have this asteroid belt debris field analog that could come in later and make this thing habitable. So I will put up my conclusion slide now because I see that basically over time. But in conclusion, this is still very much a work in progress. It is very easy to form these short period rocky planets around M-dwarfs that we observe a bunch of that might be habitable, but like I said, they might face a myriad of hazards and lose their primordial atmospheres. Our simulations show that they could be very wet if they form in situ. They might not, because this is, again, something that we don't fully understand for the Earth. Now, we also looked at delayed bombardment as a source of reconstituting a secondary atmosphere, and the outlook is still a little bleak, but if you put a giant planet out there, it could be a lot better, right? So we're looking into finding Earth-sized planets in the habitable zone with not like a solar system giant planet configuration. We're not going back to like, well, we need to find the solar system, but it'd be great to find an Earth with like a Neptune or a Saturn mass friend out there that can lay down some orbital resonances to perturb some material in. And in the future, be able to look at this from the RV side of things, be able to look at this from the debris disk side of things, and really better understand, habitability in these systems. So that is pretty much my talk. And I'll take any questions.
That was great, Matt. Thank you so much. Really, really interesting stuff. So yeah, we do have a few questions in chat, and anyone else is welcome to raise their hand or post their questions in chat if you have any. But the first one here is from Samuel, who's curious regarding the migration of Neptune-sized planets. If a Neptune-sized planet migrates sufficiently close to its M-dwarf host, is its atmosphere completely stripped? Are these potential source of Earth-sized planets in the M-dwarf systems?
Yeah, I mean, definitely, right? I'm a big proponent of, all these processes. You don't have one process that explains every different, stellar mass, right? So just like when you run this in the solar system and you have Jupiter's core migrating in, sometimes it migrates all the way in. Sometimes Saturn doesn't catch up. It's a very stochastic process. So surely, sometimes you form a larger core, it migrates all the way in, its atmosphere gets stripped, it becomes like a sub-Neptune, a hot sub-Neptune or something like that. That most definitely happens. Sometimes, maybe if you're able to form two cores, just like in the solar system, they don't migrate all the way. They come into resonance, and then you get that like Neptune at 1 AU or something with some debris that can form terrestrial planets. I think this is definitely something that we don't fully understand, but I would really be a proponent of, all these different evolutionary pathways, just like when you try and study this around solar type stars, there's not one dominant evolutionary pathway. There kind of is, super Earth formation's kind of preferred, but you get all the different outcomes.
That's interesting. Thank you. I guess I was also wondering about I'm not an exoplanet scientist. I study cosmology, but like the time scale. So these migration periods are towards like the very early part of a star system's formation. This couldn't happen after, say, the 1 billion year like settling in period has happened. Like the migration would occur much earlier.
Yeah, you need gas around to drive the migration. We think that lasts maybe 10 million years at the most. So all reshaping that's going to happen after gas. Now you can have planetesimal driven migration. It's not as extensive, right? So if you have a big, heavy planetesimal belt, which I had some kind of other slides if I had time to talk about, but if you had a massive Kuiper belt or a massive asteroid belt, it can drive some migration, but not AUs and AUs. Just enough to kind of move them a little bit. But the most of these things are going to move around at t equals 1 billion years is going to be if they destabilize and they gravitationally scatter off each other, and that's going to destroy all the terrestrial planets to begin with. So,
okay, thank you for that.
Great. And Mike Way had a question in chat. You said that the Earth is very dry, but the estimates of water content in the mantle are all over the place, as you pointed out. So when you mean dry, are you saying that even in the highest upper limits of the mantle estimates?
Definitely even in the highest. And this is definitely, there are different, people are going to have different opinions on this. The Earth is dry compared to Mars and extremely dry compared to things that we see in the asteroid belt. So maybe then it just formed from the same stuff that Venus and Mercury did, from the enstatite chondrites that are extremely dry compared to like the ordinary chondrites, which have like 10 times as much water, or the carbonaceous chondrites. But that's hard to do in these simulations. All of this is kind of a problem in terrestrial planet formation in the solar system, is making Earth too wet. Everyone's able to hang their hat on that their model delivers water to Earth, but it's often too much water because it's very easy. With Jupiter out there, Jupiter perturbs a lot of material in the asteroid belt, and as the planets are forming, it's very easy to bring a bunch of water into the Earth. So it's not necessarily a question of like, what is Earth really, anomalous compared to, chondrites or compared to Venus and Mercury. Our models aren't good at making Earth, that dry compared to Mars and the things in the asteroid belt. So the point more is not that these other planets, might be dry or not dry. It's that this is still something that we're trying to hash out in the solar system.
That's great. And Mike also wanted to know, you're looking for giant planet orbits of 100 to 1,000 days, but what about Saturn with more than a 10,000 day orbit? It's going to be hard to find, but would it be sufficient or helpful with late water accretion?
Probably not. There's a Denks et al. Paper I cited earlier in the talk in 2019. They looked at the TRAPPIST system and they asked that actual question, right? They put in a fictitious asteroid belt, and then they put in an E planet. They play with its mass and how far away it is. And once you start to get out to like 10,000 days, the strong orbital resonances that are really going to sweep stuff in, they're just not, they don't overlay down onto that material. So, maybe that would be useful if there were other undetected planets there. But yeah, in the 1,000 day would be much more the Goldilocks spot.
Gotcha. And I was just curious, when I know the problem that you're finding is that it's hard to get these late bombardments, but in the scenarios where you do get it, I'm not familiar with the statistics, but do you balance, when you're talking about habitability, do you balance delivering, volatile rich comets or asteroids or fragments versus increasing the number of late bombardments that could, cause apocalyptic scenarios on any of these worlds that may have already had life originate?
Yeah, well, we're definitely starting to get down the rabbit hole, right? Of like, can life find a way or not? But yeah, if you look in the solar system, decayed away over a billion years or so, and then there's just sporadic delivery from the asteroid belt, that wiped out the dinosaurs and stuff like that. But the Earth was a very violent place for the first billion years or so. The whole inner solar system was. So, could that last for several billion years and then have the clock just start later? Maybe. But another problem, if there's the dynamical time scale, right? There's that variable of, how long does it take in the simulation for this stuff to clear out? And then there's also the variable of like, how much leftover stuff is there, right? And if you were implanting all this material in like an asteroid belt, small body, reservoir, if you had much more material in there, it would go on to form a planet, right? So you can only put so much in the asteroid belt before it starts to form a planet, right? So there's, there are some limits into how big of a reservoir you can have sitting out there before, it would accrete into something that's not a reservoir. So yeah, I hesitate to give a definitive answer because couldn't life find a way? Probably sure. I would like to think, but I think it'd be very difficult to push that range further and further.
Gotcha. All right. Does anyone else have any other questions for Matt? I actually had another one from earlier in your talk. Going back to when you were talking about the breaking of the resonant chains and that whole process, I was just curious, is there any kind of general time scale that when that occurs, like how long were the planets in the chain to begin with? What's kind of like the driving factors for when those get broken?
Yeah, well, this is a big question. It's something that the majority of my PhD research was about in the solar system. All this stuff is mapped from the solar system paradigm, right? We understand the instability in the solar system, and there was a huge problem for like 20 years once we realized that the giant planets went through this instability. Everyone wanted it to be coincident with the late heavy bombardment, so they wanted the giant planets to stay in one stable configuration for like 600 million years or so, and then destabilize into new configuration. And it's actually really, really hard to do this, right? Things are, if you plotted, instability time, it decays off like this, that the cumulative fraction, the majority of them are going to be in, millions to tens of millions of years. And then if things survive that, they're typically stable, and only a few systems are going to, have this very late, several hundred million year, billion year later instability. So yeah, we're really starting to hone in on thinking that these instabilities also happen very early on, just like migration. Like things, it's not a requirement that things have to form in a stable configuration. Most things do form in some unstable configuration, and then a million, 10 million years down the road, they destabilize, and then that's a configuration from there on. So all these processes have to happen, fairly quick, as we think now sort of happen in the solar system too.
Gotcha. Thank you so much. All right. Does anyone else have any other questions for Matt? If not, then I think we will go ahead and end here. Matt, thanks again for coming out and talking to us today. It's really cool work that you're working on.
Thanks so much for having me. This was great. I really, really appreciate
awesome
the opportunity.
Very cool. All right. Well, I'll see everyone in 2 weeks. Thanks for coming out today. Hope everyone has a good day. Take care.
Thanks.